So I thought I'd talk about a problem that has been known to people in kind of our field, meaning analytic number theory and automorphic forms, that kind of juncture, for a long time now. And it hasn't really changed so much for the past 30, 35 years or so. So I think it falls under this canopy of problem that I don't know how to solve or really kind of have an idea of how to meaningfully get started on. So, okay, it's about conductor dropping and subconvexity. So we should remind ourselves what subconvexity is, and then say what conductor dropping means in that context. So, so subconvexity starts with the zeta function, so the Riemann zeta function, which has this sum representation and then a product representation. N goes over the natural numbers, P goes over the primes. And it has a functional equation relating the values at S and 1 minus S. So more precisely, if you look at the gamma function at S divided by 2 times zeta of S, this satisfies a nice functional equation relating the values at S and 1 minus S.
Oh, could you write a little bit bigger? It's hard to see.
Okay. Sorry, I honestly wasn't paying attention to my writing size, and I'll try to be more conscious of that. Okay. All right, so that's the zeta function, and as we know, there are many open problems concerning, for example, where the zeros are expected to be located. So we expect them to all be on this critical line where the real part of the argument is 1/2. And then there are other questions related to how fast the zeta function grows along this critical line when it is not busy vanishing, or at least supposed to be vanishing. So you could draw a picture of kind of how big the zeta function is in between these zeros. And if you were to plot that, it would look something like this. So up to about, let's say, argument 50, you go up to about argument 3, and okay, I gotta remember how many zeros there are, but okay, I won't try exactly. It looks something like that. That doesn't get much bigger than 3 for argument up to 50. So there's this conjecture, the Lindelof hypothesis, that in fact, you can bound the zeta function on the half line by any positive power of t. So let's say t goes to infinity. And so the conjecture is that this holds for all epsilon greater than 0. That's called the Lindelof hypothesis. There's kind of an old theorem called the convexity bound that says this holds for all epsilon bigger than 1/4. And then subconvexity in this context is the assertion that it holds for some epsilon less than 1/4. And this is a theorem that goes back to, as Valentin has pointed out, Hermann Weyl, and then Hardy and Littlewood, I guess, wrote it up using Weyl's method, and then Landau wrote the paper in a slightly more general form. And that goes back to roughly a century ago, maybe plus 5 years. So around 1920, this was first shown. So it's called the Weyl bound. So just the assertion this holds for all epsilon greater than 1/6. And then there's been a lot of work improving that exponent over the intervening century. And I guess the record is still due to Bourgain, which says that you can do this for epsilon equal to 0.15, and then I forgot to look up the precise exponent before the talk, but some kind of complicated number smaller than 1/6.
Is it 13 over 84?
Say what?
Is it 13 over 84?
Yeah, I think so. That sounds right. Yep.
You say 114. Oh, 1
So you're saying 13 over 84? That sounds very familiar. So anyway, and this is bringing in all the decoupling machinery, which many people here know. So that's a long history that, you know, maybe will continue to evolve. Unfortunately, probably with no hope of quite reaching the Lindelof conjecture. So another way we could try to like improve our understanding here is to maybe not try to improve the exponents as much as we can, but rather to prove non-trivial bounds, so analogs of a subconvex bound in greater generality. And so that story requires introducing the generalizations of the zeta function. So these are what are known as L functions. And I'll try to be somewhat more specific in kind of the body of the talk, but at least at the beginning, I'll treat this as a bit of a black box and just say kind of what the essential properties are rather than giving a complete formal specification. So these are objects. So they're attached to some, if you'd like, just placeholder symbol pi, and then again some number s, that look, you know, quite a bit like the zeta function, but rather than having one factor, like the above, you have some product of many factors. So we need to think of a good letter for the number of factors. Let's say D. Some people who were out with me to dinner last night. Okay. So this is called the degree of the L function. Okay. So there's a many-to-one relationship here. So of course you can write down any expression like this for any collection of complex numbers alpha, but not every such expression deserves to be called an L function. There are essentially countably many expressions like this for very, very specific alphas that you construct in some way using automorphic forms or other machinery, that give you an object with nice properties kind of parallel to the zeta function. So for instance, for any L function, there will again be a functional equation. So the L function gives rise to, in particular, some collection of complex numbers that I'll call lambda 1 through lambda n, such that if you form a product kind of like the one on the top board here, but where you shift the gamma factors by these numbers lambda j, this again satisfies some functional equation relating the values at s and 1 minus s. So a good example of such an object would be if you take, for instance, the zeta function to the dth power, then you see that you get an object of this shape where all of the alphas are identically 1, and all of the lambdas are identically 0. So that's a simple example. Another example would be you could take zeta of s plus lambda 1 through zeta of s plus lambda d for any complex numbers lambda 1 through lambda d. So if you call this L of s, this will again have a similar shape here where the alphas are something you can read off from the lambdas and p, and the lambdas will just be the lambdas that show up here. So yeah. I just need to think about erasing, but are there any questions about just what I've said so far?
Maybe it's fair to say that not any choice of such parameters will lead to something that deserves the name L function.
Yeah, that's a good point. Yep, thank you. Yeah, the only very, very special choices here.
I mean, analytic continuation is by no means clear.
Yep. Yeah, so that's another good point. So I mentioned the functional equation, but I didn't even mention here that, you know, the fact that it converges for real part large and then analytical continues is a highly non-trivial feature that will absolutely not persist if you just choose a random collection of things like this. Okay. So then, given an L function, there's an invariant you can attach to it called the analytic conductor. So just for the purpose of this talk, I'm going to kind of restrict my universe of L functions to a rather particular subset. I'm going to assume that the finite conductor, for experts who know what this means, is equal to 1. And this is the case just for the examples that I'm discussing here. So then there's a notion called the analytic conductor, which is a number depending upon pi and s. And it's just basically the size, the products of the sizes of all the ships that appear up here. Okay, and then with that additional bit of notation, so let's say for real part of s equal to a half, so the general form of this discussion is that any L function should be bounded by the conductor to the epsilon. And then there's an analogous collection of terminology. So there's some generalized Lindelof hypothesis that should hold for these things. There's a general convexity bound, which we've known for a couple decades at least. And then it's conjectured that subconvexity holds for each of these. But that is in general an open problem. And in particular, things like the Weil bound and more generality, finer things like this are kind of generally quite out of reach. Okay, so here, this is just a conjecture, whereas for here, it's as I've mentioned in all theorem. So then I think we've, okay, we haven't defined exactly the class of objects we're looking at, but we have a rich enough collection of examples, so we could just think of shifted products of copies of zeta, for example. And we've said what we mean by subconvexity. We mean a bound like this, where you can take epsilon to be smaller than a quarter. And then that at least explains this part of the title. And so then we need to explain this part, which will connect with just explaining what exactly we know towards this bound in general. Before we do that, are there any other questions about the notation or the setup?
Why do you say conductor dropping distance with a number that's you wrote it already?
So we have the conductor. I guess we got to explain what the word drop means. It's not like just what happened to my chalk over there, but yeah.
C is a finite product. And then what's the question? The question is C to the power epsilon is satisfies subconvexity.
So the conjecture here is that this bound holds for some epsilon smaller than a quarter.
What changes if you don't make this assumption of the finite conductor?
If you don't make the assumption of the finite conductor, you just put the finite conductor right there. But I just didn't want to have to say the letter and distract us with it. Yeah. And also saying what conductor dropping means in the case of finite conductor becomes more complicated. That's another reason. Okay, so maybe I strategically erased this half of the. Okay, so I've been deliberately a bit vague about what I mean by this asymptotic notation and how uniform it should hold and things like that. So the way one thinks about this problem kind of more rigorously is maybe you fix a family of objects pi, perhaps together with an argument s, perhaps that they just lie in a sequence. And then you ask that a bound like this holds as you traverse the sequence, where the meaning of this bound here is that there should be a constant you can put there that doesn't depend upon the sequence parameter. That's the kind of way you think of it. So then it makes sense to say, for example, that subconvexity holds for a sequence of pairs pi and s. Okay. So now we can ask the question, for which sequences of such pairs do we know subconvexity? So, let for example, I think I'll use notation P be a collection of pairs, let's say pi s, as on this board here. So real part of s is a half, and pi is some object we can attach an L function to. Okay. So, so given pi and s in P, so let's set T to be the largest of the numbers that show up here in the definition of the conductor. So the maximum over J ranging from 1 through D of these numbers. So this will be some number that's, I guess, at least, okay, maybe it's at least 1/2 the way I've normalized it. And let's, I guess the interesting case for this problem is when the conductor is getting big, because we know that there are basically only finally many of these things with bounded conductor. So we're going to assume that T is going to infinity, and we'll think of T as something like an indexing parameter for this family of pairs. So it's some measure just of kind of like how big all the parameters are. Okay, so then we say that the conductor drops if, so okay, maybe I'll fix the degree. I'll say everything's of degree D. So we'll say that the conductor drops maybe over the sequence if the limit, let's say as t goes to infinity, of the minimum, okay, I can just put it this way. If we take the conductor and divide by t to the d, and this goes to 0, we'll say that the conductor drops. So now why is this a reasonable thing to think? So if this maximum is actually more or less independent of the value of j, namely if they actually all differ by some constant, maybe the smallest one is 1/1,000,000th of the biggest one, something like that. Okay, then all these factors are of the same size, so when you write down the definition of the conductor, you're multiplying together d numbers that are of the same size t, and so this ratio will stay bounded from below by something positive. So we'll say that's not the case if, okay, we can maybe find a sequence in here, or maybe take a limit for something if we want to be very precise, so that this goes to 0. Okay, so we've now defined subconvexity. We've said what it means for the conductor to drop. It means that the conductor is much smaller than it could be just based on the largest size of the parameters. And so then we have, okay, so the problem is basically, I mean the problem is quite literally, so establish subconvexity in any example where the degree is at least 3 and the conductor drops. So,
I mean, this is a very weak notion of conductor dropping, right?
it is. You're correct.
I mean,
Yeah.
probably in this, I mean, like, for such a weak conductor drop.
Yeah. You make a good point. So, let's say robustly establish subconvexity. So what Valentine's pointing to is the fact that requiring it tend to 0, but maybe if it were like t to the negative alpha for some very small alpha, depending upon the degree, then you absolutely can do something like this. So maybe we should ask that this be bounded by t to the negative alpha for some, let's say, respectable alpha, and I mean alpha shouldn't need, if d is large enough, you could take alpha to be 1 over 10 or something like that. But maybe for d equal 3, you could do with alpha equal 1 over 8 or something. There's some war of constants. I mean, what you really want to do, I'll give an example, a very concrete example here in a second, but you don't need the adjective robustly. So an example would be prove subconvexity for, so I wrote down this shifted product up here. So let's take, for example, L of S to be zeta of S times, well, let's even say zeta of 1/2 times zeta of negative S. So here, let me be a bit, this is kind of okay, I guess. Let me not write it like that. Let me just say zeta of 1/2 plus IT, zeta of 1/2, zeta of 1/2 minus IT. So this is a special case of these objects here. And so these things, if you like, you can write them as a Dirichlet series involving a sum from n going 1 to infinity of some divisor function that'll depend upon the numbers lambda 1 through lambda d of n divided by n to the s. So, so the problem is to prove something for this, and I'll just say in quotes, without using the factorization. So what that means, just a little bit more precisely, I mean, this is something that both James and Max also mentioned in their talk as a theme where you try to generalize something you know for a product of zeta functions to kind of the object you get by multiplying them together and then generalize to other automorphic L functions. So you can think of it as saying, okay, write this product in the above form as a series like this, and then don't use that the sigma have this very explicit definition as a divisor sum. So this guy here would be a divisor sum over D, let's say A1 through A D equaling n of the product of A j to the lambda j. So don't use that, negative lambda j. But instead just use some kind of property of these coefficients that doesn't depend upon that factorization. And Sorry, I didn't understand the question. Yeah, it's a constant. So you could think of, I mean, I guess the way to think of this example as above is maybe you take S to be 1/2, and then you take lambda 1, lambda 2, and lambda 3 to be respectively plus IT, 0, and minus IT. Does that make sense? Yeah.
Okay, there is no conductor dropping for D equal 1, but of course I know the answer. There is a conductor dropping for D equal 2.
Right. So, I mean, you're getting at the question of like why we impose that assumption.
People may ask why 3 and not.
Yeah, I'll come to that. I'll mention that. Yeah. Okay, but thank you. Okay. Yeah.
So convex one quarter, if I remember myself correctly, it's can be proven by Poisson summation that he explained in his talk.
More or less.
I think that's fair to say. Yeah.
How about this one?
Oh, you're asking, can convexity be proved by something like Poisson summation in general?
Yeah, more or less.
The answer is again, basically, yeah.
Depends on what you call Poisson summation.
And I mean, okay, so part of our instructions were to say what the problem is, and then another part was to maybe say why it's interesting and why people have cared about it. So I mean, I think for this class of examples, this goes back to so Sarnak and then Rudnick and Sarnak in the early 90s. So and then also Watson, Sarnak's student. So they observed that if you could prove subconvex bounds in particular this generality, that it would have applications to this problem called arithmetic quantum uniperiodicity. So if you're familiar with like Elon Lindenstrass's work, they've got him a Fields medal using ergodic theory to prove something in that direction. If one could actually prove a subconvex bound there, then one can take the dynamics out of that argument and prove an effective bound in that direction. So that's kind of, I think, the kind of classic historical motivating reason for considering these. But we can also just consider it as a pure problem in analytic number theory. Maybe that's not historically how it came about, though. Okay, so that's just a word about why it's interesting.
Can the dynamics of that problem be effectivized?
I don't think there's been.
If there were an effectivization of the dynamics, would that lead to?
Yeah, I guess it would, wouldn't it? Right? Yeah. Yeah, because they're more or less equivalent. Okay. So I hope everyone's happy with just the statement and the blurb about why it's interesting. We know what the conductor is. We know what it means for it to drop. And we have a very concrete example. So if you don't want to learn the definition of an automorphic L function, okay, of course, this isn't like, I'm not like giving you a PhD problem. So if I were, I would say you've got to learn that definition because that's the only way you can make progress on this. But okay, I don't actually know, so I'm not going to say that. But you can just try to study this object directly somehow and prove a bound for this, but keeping this kind of silly factor in there and still succeeding. Okay, so we should maybe say something about like why we phrase the problem this way. So as Philippe asked, like why do we state it for D equals 3? So I mean, there's a theorem that says basically that so subconvexity, okay, I'll say for standard L functions, which means L functions attached to automorphic forms in GLN. And so there's the Langland's functoriality conjecture that says that every L function is standard in that sense. So you can think of this as just conjecturally all of them, and it's a reasonable class that we can, in particular, prove the basic properties of the functional equation. So this holds in all other cases. Okay, still assuming, as I did at the beginning of the talk, for when the finite conductor is equal to 1. So it would be a more complicated discussion if we were to go in that direction, but I didn't want to, bifurcate the talk into an elaborate discussion of kind of other results. And
You say all other cases means when d equals to 2?
yeah, so in particular, so when d is equal to 2, I guess it was finished off in the generality I've stated by Michel Venkatesh around 2010. So in particular, I mean, building on work of Duke, Friedlander, Ivanich and company in the 90s, so they addressed the case where the conductor drops there. If I have time, I'll say a little bit about how that actually works. And then when d is at least 3, so there's a first result kind of in that situation where you don't do twists by Valentin and Blummer and Jack Buttkane, where you move all 3 parameters on GL3, but they have to stay apart and they can't drop. So no conductor dropping. And then I have a paper that does something similar in the generality I've stated here, where you just need to assume the conductor does not drop, and for general. So yeah, that's kind of the state of the art. I mean, it's pretty simple to say, okay, here's a problem we should focus on, where we more or less know every other case, at least if we restrict to the setting where the finite conductor is 1. So.
Maybe one can say why conductor dropping is the enemy, at least in many methods.
Yeah.
There is a family that you look at, and the family has a certain size. And instead of
You can give, go ahead. Yeah. No, I'm happy, yeah.
instead of bounding just one L function, you bound average over the big family. And this is good if the target, namely the conductor, is big, but if the conductor is small, then you still get the same bound, it's just useless.
All right, guys, good. So you've now heard an abstract for the next part. Very, very elegantly explained. Yes. Actually, I think that was basically all I was going to explain for the rest of the talk. I think it more or less was, right? Because, I mean, I'm not supposed to tell you how to do the problem because I don't know how to do the problem. And, it could be, there could be some embarrassingly simple way to understand the problem that does not involve the ways we've attempted to tackle it thus far, so we should leave that kind of open. Which I guess leaves us the task of just saying a little bit about what we've tried and where it's kind of fallen short. But don't be biased by this. So okay, we got to say something about how do we evaluate L functions, and then how do we estimate them? And we'll list some methods there, and then we'll explain why those cover the cases that are indicated here, but not the case here. So I guess I have a fresh blackboard. Maybe I'll start. Okay, so how to evaluate L functions? So how do we think of these? So there are a few different ways. So one is there's a kind of general complex analytic technique known as the approximate functional equation. Which says, okay, if you're interested in proving upper bounds, I mean, it says basically that L of pi s, at least in the generality we're considering, where s is of real part of a half, looks something like the sum over n up to the square root of the conductor of, so lambda of n, lambda being, I mean, more or less defined by expanding this as a series, plus some other similar term that involves the root number. So if you'd like, if you assume these things are of size 1, which at least conjecturally and in many cases provably they are, then you can get the convexity bound just by bounding the size of each term here and summing them up. So that kind of answers your question, because this is suitably interpreted some form of Poisson summation, and so it gives you a way to write it down. And there's another, I mean, completely related family of techniques called integral representations. So that's a whole theory. I mean, there are many ways you can write down L functions as integrals of automorphic forms. And kind of a prototypical example is, if you've seen the way that, Riemann, for example, proved the analytic continuation of the zeta function, he did it by showing that some integral of something like a Jacobi theta function is roughly zeta of s, maybe putting a 2 there or something like that. So there are generalizations of that technique that one can use to write these things down, and either method is a useful starting point for, if you want to, for example, numerically evaluate them, or if you want to estimate them. Okay, so now how to actually estimate L functions, and I'll say non-trivially, right? Because of course you can estimate them just by taking absolute values above, and that'll give you the convexity bound, but won't easily give you anything more. I'm going to focus mostly on the case when d is at least 1 here, because a lot of the techniques for d equal 1 don't obviously generalize. So one of them is the Weil shifting technique, where you use the fact that if you shift an interval by a bit, it doesn't change so much. And so if you can show that the coefficients of your L function mix in some sense when you shift them, then you're in good shape. This is something that is much easier to do for the zeta function than for more general L functions, because you have identities like this. That significantly simplify the sums that you're looking at after you do something like Weil differencing. So these kind of techniques, at least we haven't found a good way to adapt them in higher rank, because the coefficients are no longer multiplicative, so they don't simplify like this when you multiply one by the conjugate of the other. So the main methods that people consider, or have considered, are, at least in some form, the moment method, which is what Valentin was mentioning just a minute ago. And then, I'm actually not sure if this is a complete list or not. I mean, because, for example, there are papers written on what's called the delta method that have proven, many new results in this direction, but a lot of the times you can kind of go between the two methods in some way. So I'm not going to say much about the delta method, because it's a bit of a, at least by me, like not well understood technique. It's very simple to describe just at a mechanical level. But I'm gonna just kind of assume that most delta method applications can be folded into the moment method. And so I'll focus on the moment method here. So what does the moment method consist of? So you write down a moment. So F will be a family of pi's, and okay, maybe you take the 2kth moment of some family like this, and you try to estimate this. So maybe you conjecture, based on the Limblot hypothesis, that this has size comparable to the size of the family F. So, and I guess I've tacitly taken the point S to be 1/2 here, but as we kind of indicated in one of these earlier examples, the one you can see up there, you can always modify pi to reduce to the case that s is a half by shifting it a bit. So, okay, a basic example of this would be, okay, I've written some here, but you could consider more generally integrals. So for example, the moments of the zeta function on the critical line, the second, the fourth, the sixth moment, are examples like this. And so as was mentioned in Max and James's talks, we know how to evaluate those moments when we take the exponent to be 2 or 4, but not 6. And that's a general feature here that for the families for which we can evaluate any moments, when the degree gets higher, the evaluation becomes more difficult, and yeah. Okay, so this, of course, can be used to bound an individual term that shows up here. So if we can show this, and I put a question mark here to indicate that we often can't, then, well, okay, you get that L of pi half is bounded by the size of the family to the 1 over 2k. And now to make things a little more quantitative, so let's say that this is a family of pi's with, let's say, conductor of pi, maybe conductor of pi and a half, between, say, some number q and twice q, where q is some parameter going off to infinity. So in that case, what would you like to show? You would like to show that this is bounded by q to the 1/4 minus delta. That's what subconvexity would amount to in this situation. And so you have an estimate like this, I guess, if and only if the family is small enough in terms of the conductor. So maybe, I'll just leave it. And of course, you have a better chance of this happening the larger you take k. And so there's some range of moments where if you could estimate them effectively, you would get a subconvex bound. But for smaller moments, you don't get anything non-trivial. There's one kind of edge case when, so I guess there's this edge case where we have equality in this last expression. And so there's a technique called the amplification method that very often can be used to do a bit better. And what that method amounts to is in this estimate, not just proving an upward bound, but maybe proving some kind of robust asymptotic like this, where you have a main term and a much smaller error term by an exponent, where the asymptotic is moreover robust if you perturb the family just a little bit. And that allows you to insert what's called an amplifier. Which consists of some short sum, so say over L up to some very small power of the conductor, maybe q to the alpha, of, let's say, some general bilinear form coefficients times some coefficients involving pi. So you can choose the coefficients to bias a particular pi, maybe I call it pi naught to single it out. Okay, I guess this is a general one. So okay, you choose those to be maybe the conjugates of some particular one, and that'll amplify the contribution of one of them. But for most of them, it'll kind of dampen it, and if your asymptotic formula is robust enough, then it'll dampen the size of the main term a bit. It will not damage the error term too much, and so you'll be able to do a little bit better. So I'm mentioning this very quickly, but I know there are people here who think about additive combinatorics and harmonic analysis, where things like van der Korpitz inequality come into play. So this is a kind of a classical van der Korpit application where you're exploiting a bit of invariance of something and some kind of mixing to dampen a main term at the cost of blowing up an error term a little bit. Okay. But yeah, fundamentally, the main engine driving these bounds has been asymptotic evaluations of moments in certain cases. So either in cases where you can do sufficiently better than convexity just by taking the moment large enough, or you can get right to the edge and then throw in an amplifier and then do a little bit better that way. Okay, so that's kind of the very general strategy, and I mentioned down here how you can evaluate L functions. So you can take any of these ways that you can evaluate L functions, plug those into the moment that you're trying to estimate, and then try to estimate it that way. And so, you know, when you do that, you'll either be faced with, say, bilinear sums over pi of quantities like this, or maybe some average over pi of some integral representation like this. And, you know, in those two cases, you can appeal to trace formulas that give you formulas for averages of these coefficients, or you can appeal in this setting where you use an integral representation to something like a Parseval type identity. That's another common technique. Okay, so now that's like the kind of completely general strategy. Try to estimate some moments where the degree is large enough. And so I don't have a huge amount of time left, so maybe I'll focus the discussion a bit. There are basically 4 families of moments that we know how to estimate that are relevant for subconvexity. So there, you know, maybe this isn't 100% precise, but I'll say there's roughly 4 infinite families where we actually know how to carry out this kind of strategy. So one of them includes, for example, the 4th moment of the zeta function. Okay, so that's a situation where we can get an asymptotic formula, as many people here know, and we could amplify it if we wanted to, and that would be one way to get the subconvex bound for zeta. And I mean, there's also like a GL2 analog of this where you replace zeta to the 4th with a GL2L function to the 2nd power. And okay, I guess there is a generalization of this that, you know, so I mean, this is kind of for GL2 and GL1. There is more generally something you can do similarly for GLN plus 1 and GLN. Maybe you have pi and sigma on the 2 of them, where you consider an average over sigma in a, well, called dyadic family. So dyadic family means kind of something of comparable to like an interval between 0 and t, or maybe t and 2t, rather than something much shorter, of L of pi times sigma 1/2. And so this is something that, so something kind of like this is treated in my paper with Akshay Venkatesh. And I mean, there's actually a hope of making, I mean, we give an ineffective estimate, but there's now a hope of making it effective. So it's something that should be available. It'll be kind of a general form of this kind of estimate. But unfortunately, I mean, you see here the inequality relating the family size and the conductor. So here,
That would be making use of recent progress in effectivizing.
yeah, exactly. But even assuming that, one could never use this technique to treat a conductor dropping case. So, okay, but the unifying theme will be that all of the families I discuss here fail to apply to the conductor dropping case. So maybe the parameters will again be of size t, kind of like over here. So the conductors will typically be as large in this setting as t to the n times n minus 1 over 2. And the family size will be I get this right? So the now the conductors here, doing it the other way around, will be n times n plus 1. The family size will be, so the size of the dyadic family on GLN is t to the n times n minus 1 over 2. All right. And if you, well, okay. I'm suddenly feeling puzzled that I'm seeing a plus there and a minus there, but okay, just thinking, so you'll have n plus 1 times n parameters here. You'll have 2k equal to 2. And so the edge case here is when the family size is exactly q to the root over 2. Yeah.
So this upper bound is when you do not drop.
Yeah, this is when you do not drop, exactly. Yeah.
So you could achieve subconvexity.
Well, we can achieve subconvexity when the conductor does not drop.
If you have this bound.
Exactly.
So which is okay.
So the point I'm just going to make, maybe completely ignore the numerics that I'm attempting to create on the fly, and just say, okay, this is in the edge case for subconvexity if and only if the conductor does not drop. That's like a clear way of saying it. So if the conductor dropped here, the exponents would just not align. They barely align in the conductor not dropping case. And so, in that case, you're going to kind of be very, very far from your target. And if you amplify or whatever, you're not going to win by enough to overcome the huge deficit you've lost from the conductor dropping. So that's one example. There are other examples that are, I'll just kind of briefly indicate them, but it's going to be exactly the same story for each of them. So there's another one where you take GL n plus 1 and GLN. So again, maybe pi and sigma are the symbols on them. And you sum over pi in what I'll call a short family. So short family means all of the parameters will live in windows that look roughly like numbers between t and t plus 1, at least something kind of like that. And you again look at the moment of L of pi times sigma 1/2 squared. So the numerology that I've anyways omitted will be a little bit different, but it'll come out to the same conclusion that you're at the edge case for subconvexity precisely if the conductor does not drop. And so, again, you can get a subconvex bound when the conductor does not drop, but when it does drop by a good amount, you fail to achieve anything. And then, since I got some room here, so, okay, a third case would be like the papers of Ivich and Conrad Vaniach and Petra Young. So this involves a sum over pi on PGL2. This is like GL2 with a condition where the parameters sum to 0. And okay, you take again a short family, and you use the fact that the L functions are non-negative to work with an odd degree moment. So this is a case where this is very good for proving a strong quantitative subconvex bound. So for example, this is how the Weil bound is proved in general for Dirichlet L functions. But okay, in these kinds of families, the conductor never drops anyway, so it's not. And okay, I can imagine generalizations of this where maybe you work with higher degree special orthogonal groups rather than SO3 here. But again, for those, you're going to have the same situation where maybe the conductor does drop, but you're exactly at the edge case for subconvexity when it doesn't. So you, yeah.
So it never drops to have positivity. Oh, okay, you say it's big.
So,
Okay.
so what you can check from a back of the envelope is that if you have like any collection of parameters where like one of them is 0, you will never be able to achieve that by even the wildest hypothetical generalization of Conway-Ivanich that I can imagine. And then the fourth example.
What I say, you could imagine cubic moments not on PGL2, so what I say, you would not have necessarily the positivity.
Oh, okay. So I have in mind, for example, doing like a like a fifth moment on SO5 where you have positivity, or a seventh moment on SO7. So, okay, even assuming that one could do that, if you work out the numerology, again, you would not do anything better than trivial when it drops. And then the fourth kind of family of moments that we can evaluate that are relevant for subconvexity is the fourth moment for GL2. So this will again be, I mean, it's kind of like a short family, but it's more, well, okay, I'll just say, it's the short family case that is relevant for conductor dropping of the fourth power here. So this is something that was done by Dupré and Ivanich in some generality, and then Michel Venkatesh more generally. And so, I mean, this you can think of as kind of like this in the case where n is 1, but you replace the exponent 2 with the exponent 4. And so it's just kind of the general principle that, yeah, okay, if you take a higher degree, then you don't need the conductor to be as big in order for this right-hand side to be bigger than the family size. So, okay, it's a situation where, I mean, okay, of course you can try to do this in every situation. You can try to compensate for the conductor drop by taking a larger degree moment. But the proof is very GL2 specific, so it uses an algebraic feature of GL2 so it uses the fact that you have something called the triple product formula for integrals of Waterborg forms in GL2, which is a very specific feature. So I don't want to get into more technical details on that. And I think I've explained done my basic job of just saying where the techniques roughly fall short. And of course, there's a natural thing to try, which is like, well, okay, just try doing higher moments more generally. And so this is something that, I have been trying kind of, for a while, but there's no kind of clear path there. So any original approaches would also be